Gibbs free energy, lecture number 27. So this is the last lecture of the semester. We're going to finish up by talking about this last thermodynamic principle, Gibbs free energy. Right? So we saw before that we could talk about enthalpy, the heat transfer in a reaction. This delta H value didn't directly relate to spontaneity. Next, we talked about the entropy, this amount of disorder or randomness within the molecules, and again, we saw that we can have spontaneous reactions that either increased or decreased the entropy value. So in this section, we're going to actually finally talk about what makes or directly relates some thermodynamic variable to spontaneity, and that's through this Gibbs free energy. So in a spontaneous process, remember that the entropy of the universe is always increasing. So delta S of the universe always has to be positive. If a system's at equilibrium, right, so both the forward and the back reactions, reverse reactions, are happening at the same rate, then the entropy of the universe shouldn't be changing because it's going back and forth. So the entropy of the systems plus the surroundings should be zero. Right? But we can then take that a step back and talk about this free energy, which we're going to call G. Right? If we talk about the free energy of the system being equal to the amount of heat that's transferred plus the temperature times the entropy of the system, this delta S of the system, right? That's going to take these values that we know and going to relate it to this free energy. So this free energy delta G is the delta H of the system minus T delta S. So when we get a value, delta G value of less than 0, a negative number, then that reaction is going to be said to be spontaneous in the forward direction, or the spontaneous as it's written. If it's then positive, greater than 0, we see that that's going to be non-spontaneous. It's not going to happen as written. But if it's non-spontaneous going in one direction, then it should be spontaneous going in the other direction. So all these non-spontaneous reactions that we see are going to be spontaneous then in the opposite direction. If we see that delta G is 0, this free energy change is 0, then that system is at equilibrium. Right? So now we can relate spontaneity to this enthalpy and entropy with some effect of temperature. And we're going to see that when we combine these three things, we have one of three possibilities that can occur. Either the reaction is always going to be spontaneous as it's written, it's never going to be spontaneous as written, or because we have this value of temperature in there, it can be spontaneous in some temperatures and non-spontaneous at the other. So we're going to break down this delta G equation then and look at those different times. Right? So if we want this delta G, which is equal to delta H minus T delta S, in order to get a positive delta G, right, that's going to happen when we have a positive delta H and a negative delta S. Right? Because when we take that negative times the negative, we're going to get a positive. So that's always going to be positive. So when we have a negative delta H and a positive delta H, that one is always non-spontaneous. It's listed here. If we reverse those, where we have a negative delta H and a positive delta S, then it doesn't matter what temperature we're at in this equation, we're always going to get a negative value. So negative delta H, positive delta S, always is going to lead to a spontaneous reaction. It's in these two cases where the signs are the same, either both positive or both negative, that the outcome of G is going to depend on whether temperature is high or low. So if they're both positive, as you can see here, then at some point that negative, or the temperature times the entropy, is going to outweigh this enthalpy reaction, and it's going to become spontaneous. So as you can see on the top here, both positive, we get at high temperatures, we're going to get a spontaneous reaction. Right? What high temperature is, that's sort of one of those, it's at high temperatures, but what that means is sort of nebulous. And if we look down here at the bottom, where we have both of them negative, it's going to be spontaneous until, again, this side of the equation, where we have the T delta S, becomes bigger than the delta H value. So then it's going to become non-spontaneous. So both negative is going to be spontaneous at low temperatures. So we have this, depending on those two values, we can then predict or calculate delta G, but based on their signs, we can sort of determine whether it's going to be always spontaneous, never spontaneous, or spontaneity dependent on temperature. When we look at these values, the one that's determining the delta G value is going to be what we call driven. So if we look at where they're both positive on top, it's going to be spontaneous when the delta S becomes, or the temperature becomes large. So that's an entropy-driven process. If we look down here at the bottom, when they're both negative, it's going to be spontaneous until because of the enthalpy, until that temperature becomes so high that positive comes into effect. So this bottom one, where they're both negative, is what we call an enthalpy-driven process. Right? So those two terms are going, which one is making it spontaneous or making it negative. We don't have that case in the always or never spontaneous. So let's look at an example real quick where we do this calculation. What is the free energy change for the following reaction at 25 degrees Celsius? Right? So we take N2F4 as a gas, go to 2NF2 as a gas. Right? Do the calculations, or we see that the delta H for this reaction is 85 kilojoules. The delta S is 198 joules per K. Then we can calculate the delta G here as being, again, we have to have them in the same units. So let's convert the delta H to joules. So we have 8.5 times 10 to the 4th joules minus the temperature, which is 298.15 K, times the entropy, 198, gives us a value of 2.6 times 10 to the 4th joules. Right? A positive number, which means that this reaction is not spontaneous at this temperature. Right? We could calculate, because they're both positive, we could calculate a temperature where it could be spontaneous, but we'll save that for later. So taking those information that we had before, the delta H and the delta S, we can now calculate this new value of delta G, this free energy. So let's talk a little bit about this free energy. It's, again, a state function. So we can calculate it just the way we calculated the other state functions, with the amount of free energy in the product state minus the amount of free energy at the reactant state, or the sum, right, just like before, the final conditions minus the initial conditions. And like enthalpy, we can't measure free energy of a given substance. We can only measure the change in those values. So we've come up with a standard free energy of formation again, very similar to the way we did standard enthalpy of formation. So same process. We're forming 1 mole of a compound from its elements in their elemental form, which means, just like in enthalpy, things that are in their most stable elemental form are going to have a delta G of formation of 0. Right? And then we'll calculate everything else from those values. Again, so as we've seen in class already, that we see those tables that have the 3 thermodynamic variables, the delta H, the delta G, and the entropy, or S value. Right? So we'll look them up. So we can do a calculation just like we've done before when we look at C6H6, 2 of those, plus 15 oxygens to form 12 carbon dioxides and 6 waters. We could calculate that just like we have before. Right? 12 times the value, which is a negative for the carbon dioxide, negative 386.2, plus 6 times the value for water, which is negative 237.192. Add those together, minus the sum of the reactants, which is 2 times the value for the C6H6, which is 124.5, plus the 15. Again, oxygen here is an elemental state, so it has a value of 0. Do that calculation just like we have before. We get a value, again, of a negative 6.3 times 10 to the 3rd kilojoules. Now we get a negative value for free energy, or delta G, which means that our reaction is spontaneous. Negative values for delta G means our reaction is spontaneous. Right? So we go back to that other state where there's some cases we can have a spontaneous reaction, and in other conditions we can have a non-spontaneous reaction. We can then solve for when that takes place using this simple value. Right? So if we look at delta G is equal to delta H minus T delta S, if the moment it transfers between negative and a positive value, to make that transition we have to go through zero, or that equilibrium condition, right, where both the forward and the reverse are just as likely. So if we set this equation equal to zero, then we can, if we plug in our delta H, which we know, and our delta S, which we know, and we can then simply solve for T. Right? So if we look at this reaction where we take calcium carbonate solid is in equilibrium with calcium oxide plus CO2, we see that the temperature at which this changes into spontaneity, right, is this 385 degrees Celsius. Right? When we calculate it again, it'll be in Kelvin, and then we can do a simple conversion. So we can calculate the temperature at which these transition occurs using this equation, delta G minus delta A, or equals delta H minus T delta S. Right? And then we can also, if we are at equilibrium where this delta G is zero, we can then predict what temperature the entropy changes based on the enthalpy. Right? So if we look at this free energy change of a phase transition going from a solid to a liquid, or a liquid to a gas, at the phase transition, at those temperatures, we see that we get both processes are just as likely. A substance going, for ice, for example, water at 0 degrees Celsius, it's just as likely as a water molecule will come together and form ice as an ice molecule or solid water will dissociate into the liquid form. Right? Both of those processes are about as likely, so we would get then a delta G value of 0. Doing that, we can then calculate what this entropy change will be from that. Right? So here we have, instead of the solid, the melting point, we're at the boiling point. So we have the different delta H value of 40.79 kilojoules. The boiling temperature for water is 373, so we get then the entropy change of this phase change being 109 joules per K. Right? All because these two are in equilibrium. Which means there has to be some relationship between this free energy and chemical equilibrium. Right? And we can see that here, this free energy change of a reaction under any condition is equal to the free energy change of the reaction under standard conditions plus RT natural log of Q. And we'll talk more about Q next semester. But when we talk about something at equilibrium, the difference between where it's under standard conditions and not is going to be 0. So this delta G value under non-standard conditions is going to be 0. So we can relate this then that this free energy change under standard conditions is equal to a negative RT natural log of K, where K in this equation is going to be equal to the information about that equilibrium. Right? So if a reaction proceeds spontaneously, which means that there's likely it's going to go from the reactants to the products, we would predict that this delta G would be negative and K is going to be large. So this case occurs. Right? If it's the other way, where delta G is, if it's a non-spontaneous reaction greater than 0, then we would predict that the reactants are more likely to form, so K is going to be a value less than 1. Right? So at equilibrium, this K value becomes 1, and we have delta G is equal to 0. So then we can use this equation delta G naught, or under standard conditions, is equal to a negative RT natural log of K to determine these equilibrium constants. Right, so if we look at this reaction here, the first thing we have to do is calculate the free energy change using products minus reactants. We see if we do that, we get 86 or 85.86 kilojoules. Right? Then we plug that into our solve for K. The natural log of K is equal to this delta G value over negative RT. Plug in those values, we get then K inverse log to calculate for K. We find that this equilibrium constant for this reaction is going to be 8.95 times 10 to the negative 16th. It's a value less than 1, which means that this is going to favor the reactants. And we can see that as well because if we look at the delta G value, that value is positive, which means this reaction is not spontaneous. So we can see those two are related. If the K is large, much larger than 1, it should be a spontaneous reaction. If K is much less than 1, it's a non-spontaneous reaction. Right? We'll talk more about these equilibriums in the next semester, but right now just understand that those two are related, and we can do the algebra to solve between them.